two quantities trade back and forth. U1 pumps into U2 and U2 pumps back into U1. The system obeys the differential equation du dt equals A times U, where A is the matrix with rows -1, 2, and 1, -2. You might expect messy calculus. Instead, just two numbers and two arrows, the eigenvalues and eigenvectors, will tell you the entire future of this system. Let's start with the scalar case. The equation du dt equals A times. U has the solution U of t equals c times e to the at. Exponentials solve constant coefficient linear differential equations because differentiating an exponential returns the exponential multiplied by its exponent. That is exactly the property we need. So for a vector system, we try the same shape. U of t equals e to the lambda t times a constant vector x. Now let's plug this gas into the equation du dt equals A times U. Differentiate the left side. The time derivative of e to the lambda t times x is lambda times e to the lambda t times x because x is a constant vector and the derivative just brings down a factor of lambda. The right side is A times e to the lambda t times x. Since e to the lambda t is just a scalar, we can pull it out in front, giving e to the lambda t times ax. Now both sides share the factor e to the lambda t, which is never 0, so we can cancel it. What remains is ax equals lambda x. This is the eigenvalue equation. So the exponent in our solution must be an eigenvalue of a, and the coefficient vector must be its eigenvector. Our differential equation has become a linear algebra problem. Our strategy is now clear. First, find the eigenvalues and eigenvectors of A. Each eigenvalue-eigenvector pair gives us one pure exponential solution. Then we superpose them and finally fit the initial condition to determine the constants. For our problem, the matrix A has entries -1, 2 in the first row and 1, -2 in the second row. The initial condition, U of 0, is the vector 1, 0. Let's begin by finding the eigenvalues. Look at A. Notice that column 2 is -2 times column 1, and that means the columns are linearly dependent, so A is singular and its determinant is 0. A singular matrix always has 0 as an eigenvalue, so lambda 1 equals 0. For the second eigenvalue, we use the trace. The trace is the sum of the diagonal entries, -1 plus -2, which equals -3. Since the trace equals the sum of the eigenvalues, we have 0 plus lambda 2 equals -3, so lambda 2 equals -3. Let's verify with the characteristic polynomial lambda squared minus trace times lambda plus determinant. That gives lambda squared plus 3 lambda, which factors as lambda times the quantity lambda plus 3. The roots are 0 and -3, confirmed. Now let's find the eigenvectors. For lambda 1 equals 0, we solve A times x equals 0. Using matrix A, the first row says -x1 plus 2, x2 equals 0, which rearranges to x1 equals 2x2. Picking x2 equals 1 gives the eigenvector 2, 1. For lambda 2 equals -3, we solve the matrix A plus 3 times the identity times x equals 0. Adding 3 to each diagonal entry, A plus 3, I has 2, 2 on the top row, and 1, 1 on the bottom. Both rows give the same equation, x1 plus x2 equals 0, so x2 equals -x1. Picking x1 equals 1 gives the eigenvector 1, -1, 2 eigenvalues, 2 eigenvectors. That's everything we need. Now let's assemble the general solution. We write U of t equals c1 times e to the 0t times the vector 2, 1 plus c2 times e to the -3, t times the vector 1, -1. Let's simplify. Note that e to the 0t equals 1, always. So the first mode is constant. It doesn't decay at all. This gives us the cleaner form. U of t equals c1 times the vector 2, 1 plus c2 times e to the -3, t times the vector 1, -1. The first term is the steady mode, and the second term is the decaying mode that shrinks to 0 as t grows. Now apply the initial condition. At t equals 0, e to the negative 3, t equals 1. So u of 0 simplifies to c1 times the vector 2, 1, plus c2 times the vector 1, negative 1. This must equal the initial vector 1, 0. Matching components gives two equations. The first component reads 2, c1 plus c2 equals 1. The second component reads c1 minus c2 equals 0. From the second equation, c1 equals c2. Substituting into the first, we get 2c1 plus c1 equals 1. That is 3c1 equals 1, so c1 equals 1/3. Therefore, c2 also equals 1/3. Both constants are 1/3, and we can now write the complete solution. U of t equals 1/3 times the vector 2, 1 plus 1/3 times e to the negative 3, t times the vector 1, negative 1. Let's write out the components explicitly. U1 of t equals 2/3 plus 1/3 times e to the negative 3t, and U2 of t equals 1/3 minus 1/3 times e to the negative 3t. Let's verify the initial condition at t equals 0. Since e to the 0 is 1, u1 of 0 is 2/3 plus 1/3, which equals 1, and u2 of 0 is 1/3 minus 1/3, which equals 0. So the initial condition 1, 0 is matched perfectly. Watch what happens as t grows. The term e to the minus 3t decays to 0 quickly. By t equals 1, it's already about 0.05, and it keeps shrinking, so everything involving the second eigenvector dies away. What remains is 1/3 times the vector 2, 1, which gives 2/3 and 1/3. And that's the steady state. U1 starts at 1 and drops smoothly down to 2/3. U2 starts at 0 and rises smoothly up to 1/3. Notice the sum. U1 plus U2 equals 1 for all time. Mass is conserved, which is exactly why 0 was an eigenvalue in the first place. The 0 eigenvalue sets the steady state, and the negative eigenvalue, -3, sets how fast we reach it. The eigenvalue signs tell the whole story. Well, when lambda is greater than 0, e to the lambda t blows up. That's growth. Right? When lambda equals 0, e to the lambda t equals 1, a steady state. Right? When lambda is less than 0, e to the lambda t decays. Exponential decay. The same eigenstructure powers difference equations through a to the kth power, and the differential equations through e to the at. Eigenvectors decouple a coupled system into independent scalar pieces, 2 numbers and 2 arrows, and the entire future falls out.